Giant Magellan Telescope is one of the largest and most advanced telescopes ever designed. So you probably have a lot of questions about how the telescope works and what kinds of discoveries it will make. Well, you're in luck. We've assembled a few experts to answer some of your most frequently asked questions about this amazing feat of engineering. Here we go. GMT is being designed to enable huge leaps in all areas of astrophysics, but one of the things that I think will be the most exciting will be the work we can do to understand planets beyond our solar system. So we're building two unique spectrographs that will let us study not just the parent stars, but the atmospheres of the planets themselves. And if we see key molecules like methane and molecular oxygen in the atmosphere of a planet in the right combinations, then we'll know that that exoplanet hosts life. So we already know that there are tens of billions of planets in the Milky Way that could host life. But if we directly observe the chemical signatures of life in just one of them, I think that will change what we think it means to be human. And that's pretty exciting.
The GMT is being built in Chile's Atacama Desert, one of the highest and driest regions on Earth. Our construction site, Alaskan Panas Peak, has an altitude of over 2,500 meters, or 8,500 feet. The GMT will have spectacular conditions for more than 300 nights a year, with some of the best astronomical seeing on Earth. The location of the GMT offers key advantages in terms of seeing, number of clear nights, altitude, and dry weather.
I'm asked what sort of enclosure is required for the GMT telescope. First of all, the GMT requires a weather-tight enclosure to protect the telescope from the sun, rain, snow, and other inclement weather. The upper portion of the enclosure has to be able to open using its shutter doors and rotate on wheels in order to follow the telescope as it tracks objects across the night sky. The GMT enclosure is roughly cylindrical in shape, about 60 meters in diameter and about 65 meters tall. That's about the height of a 22-story building. The rotating mass of the enclosure is about 4,200 metric tons, or 9.3 million pounds. And at top speed, the outer edge of the enclosure can rotate, do a full revolution in about 3 minutes. And this is about 2.5 miles an hour at the outer radius of the enclosure. So from these numbers, we can conclude that the GMT enclosure is quite a substantial piece of equipment.
The GMT Mirror Simulator is a round piece of steel weighing approximately 14,000 kilograms. Underneath the Mirror Simulator is an array of interface features that attach to mechanisms that support and control the mirrors. This includes the single and triple actuators, the hardpoints, and static supports. The mirror simulator will be used to validate the hardware and software of the mirror support system.
The astronomer must write a compelling description of the science he or she would do with the telescope time, why that science is important, and why it requires that specific telescope. All the proposals submitted by astronomers are then reviewed by a panel of experts who rate them according to scientific merit. The telescope time is so popular that only 1 out of every 4 or 5 proposals gets awarded telescope time.
The GMT will be built at the Las Campanas Observatory in Chile, in one of the most seismically active regions in the world. The service life is 50 years, so we have designed the telescope and enclosure to withstand large earthquakes. The telescope sits on 24 friction pendulum bearings located at the base of the telescope pier. The bearings each have an articulated slider that can move along a concave surface. The shape of the sliding surface results in a pendulum-like motion that decouples the telescope from violent ground motion, and the friction limits the amplitude of the pendulum swing. These devices are common in modern construction in seismically active regions, and if you ever have the opportunity to see the Space Shuttle Endeavour at the California Science Center, you'll notice that it sits on friction pendulum bearings.
The ground layer of atmosphere is a large contributor to the degradation of seeing. That is how well we can resolve objects we are observing. The GMT has a system called ground layer adaptive optics, which can correct these atmospheric distortions over a large field of view. However, we have evidence that the very large structure of our telescope can have an impact on the ground layer. We are doing complex and advanced simulations to understand this local layer and help us guide to design an efficient adaptive optics system.
Hello, I've been asked to explain what is meant by the term telescope mount. We all understand that a telescope is a device that studies faraway objects, and when we look through an optical telescope with an eyepiece, that faraway object looks much closer. But most people don't know that astronomers and engineers use certain terms to label specific parts of the telescope, such as the optics, which consists of the mirrors and the lenses, the instruments, such as a camera or spectrograph, and the mount. The telescope mount is that part of the telescope that contains the supporting structure and motion drives to move the telescope. Thus, the mount holds the optics and instruments firmly and very precisely in place to make observations of celestial objects in the sky as effective as possible. For the Giant Magellan Telescope, or GMT, the mount by itself has a mass of 1,800,000 kilograms, is approximately 35 meters tall, and it holds the primary optics consisting of 7 8.4 meter diameter mirrors. Yes, the GMT really is a giant. The fully assembled telescope has a mass of about 2,100,000 kilograms, sits on a very thin film of oil, only 50 microns thick, as it moves smoothly and efficiently to study objects in the sky. Thank you.
Astronomy involves the study of objects that are far away and very faint. You've got to collect a lot of light and focus it into as sharp an image as you can. And that's what telescopes do. They gather and concentrate light. And that's why the history of the telescope is the history of how to build the largest light-collecting mirror or lens. The new generation of telescopes form their light-collecting mirrors out of individual mirror segments that are computer-controlled so that they behave like they're part of a single large mirror. The Giant Magellan Telescope uses 7 mirror segments, each 8.4 meters in diameter. These are the largest mirrors in the world. In addition, GMT features 7 adaptive mirrors of about 1 meter in diameter that are bent into complex shapes by high-speed computer control to remove the twinkle from starlight that's introduced by the Earth's turbulent atmosphere. These features will provide the Giant Magellan Telescope with capabilities far beyond any prior telescope, and the power to probe the heavens, to search for an understanding of how the universe came to be. What is the nature of dark matter and dark energy? Do the planets orbiting nearby stars have atmospheres that can sustain life as we understand it? We stand at the threshold of an exciting journey of discovery. The universe awaits.